So today we're going to talk about the barrier method. This is our second lecture in the second order method unit. This is also the last lecture before spring break, so I guess you guys are looking forward to this one being done with. Then you get a week off. So let's see, if I'm remembering correctly, you have a homework due tomorrow. It's due at 4 p.m. And we're going to release the next homework tomorrow. Don't party too hard over spring break because you have a homework due the week you get back. Unfortunately, that's the way it worked out. I think that was always the way it was according to the schedule. It's just that we originally had you turn in the homework on Tuesday this week, so it would have given you a little more time. But we've made this homework a little bit shorter. At least two of the questions are quite short. So you should find this one shorter and make sure to look at it over spring break. Otherwise, the week after you get back might be a little bit hectic. So it's due 2 weeks from Thursday. So we're releasing it tomorrow, and then it's due in 2 weeks from then. Any questions before we begin with the barrier method? Yeah?
Alex published a book.
Wow. That sounds like more of a comment than a question, but that's pretty impressive. Congratulations. We'll have to take a look at it. Any questions? Okay, so we're going to talk about the barrier method today. This is I like the barrier method. I think it's a pretty intuitive idea, and you'll see it really. It opens up the scope of problems you can solve with second order methods quite a lot. So just to remind you of what we talked about last time. We talked about Newton's method last time, which we went back to this kind of basic setting we studied with gradient descent, which is that we have a smooth convex function we want to minimize without constraints. And like gradient descent, we saw that there's a method we could use called Newton's method. It's like gradient descent because it uses quadratic approximations to the function at each step. It's unlike gradient descent in that it uses the Hessian of the function to form that quadratic approximation. And gradient descent only uses the identity matrix as the Hessian times some constant 1 over t. So we saw that Newton's method actually has, in a sense, a lot faster convergence than gradient descent. And it looks like I make some guess to where I start, x naught. And then at step k, I look at where I was before, at step k minus 1. And I solve a linear system in the Hessian. So I solve the Hessian times some vector v equals the gradient. I solve that for the vector v. That's the Hessian inverse the gradient. And I take a step along that direction. You can think of this as minimizing a quadratic approximation. So two-term approximation to the function, where the quadratic form is actually using the Hessian that we see at that point. The step sizes are usually chosen by backtracking. It's the same strategy we've used in first-order methods. Some people use pure step sizes in Newton methods, but that's very rare. So a pure step size means to take all of these equal to 1. So in Newton's method, remember we said these have kind of a natural scale. Taking this step size equal to 1 means I'm doing a full quadratic approximation, and I'm moving fully to the minimizer of that quadratic approximation. That's called pure Newton's method. It doesn't converge necessarily. Under very general conditions, Newton's method converges with backtracking, and it gets a fast local convergence rate. We saw that it was log 1 over epsilon iterations to get to within epsilon accuracy in terms of the criterion difference. So that was just a brief overview. What are the downsides of Newton's method? Well, there's two of them. The first was that it requires solving linear systems in the Hessian. And the second was that we can only handle equality constraints we saw in the last lecture. So the first one is a real concern, because if the Hessian's dense, and I'm in n dimensions, so the Hessian's n by n, then a linear system in the Hessian takes about n cubed operations, n cubed flops to solve. That's very prohibitive for Newton's method. It means we can't really solve generic large-scale problems. A fix for that is to use what are called Quasi-Newton methods. And I'm going to very briefly go over that right now. The second issue was that we couldn't handle inequality constraints with Newton's method. I told you that projected Newton's method wouldn't really work. We can't just project on a constraint set. That's where we're going to remedy this lecture with what we call the barrier method. So let's just quickly go to the Quasi-Newton part we didn't cover last time. Quasi-Newton methods are pretty interesting. We could probably spend several weeks on them. They were at one point quite a popular topic of research. I think it's cooled down a bit, but people still use Quasi-Newton methods quite a lot. So Quasi-Newton methods come into play when the Hessian is either too expensive to compute, or it's too expensive to solve a linear system in the Hessian, or it's singular. That's another issue that we run into. We didn't talk about what happens if the Hessian is singular, right? If I get to a point where the Hessian is singular, I can't solve. There's not a unique solution to that linear system. So Quasi-Newton methods are kind of a class of methods that approximate the Hessian with some other matrix H that's strictly positive definite. And then we update according to that matrix H. So instead of using the full Hessian, we use some matrix H that's computed at each step. So we recompute that approximation to the Hessian. The goal is to make a linear system in H cheap to solve. So I want to be able to choose H so that H times V equals, the gradient is cheap to solve. And also cheap to store, because often with very large problems, if the Hessian's dense, then n-squared storage might even be too much to handle. Convergence is very fast with Quasi-Newton methods. It's super linear. So some of the basic results say that Quasi-Newton methods converge in linear time. Remember, that's what we saw with gradient descent under strong convexity. Even stronger results say they converge in superlinear time, so that means faster than linear time, but they don't converge at a quadratic rate. So it's somewhere in between log of 1 over epsilon and log of 1 over epsilon, those two extremes being achieved by gradient descent and Newton's method. But they're still very fast. Roughly n steps of a Quasi-Newton method make the same progress as one Newton step. That's a rule of thumb you can remember. Okay, so if I do this n times, then I'm making as much progress as one Newton step. But it could be that this is actually much cheaper one of these could be much, much cheaper than a Newton step. Right? This could be order n, and Newton step could be order n cubed. So that's a pretty favorable trade-off. There's a huge variety of Quasi-Newton methods. I'll just talk about two of the most basic ones, and we're not going to go into any details. I've given some nice references at the end you can go into to look if you want to implement one yourself, or if you're curious to know what they look like in detail, take a look at those references. The common theme among all Quasi-Newton methods is to propagate the computation of H across iterations. So I don't want to recompute my approximation anew when I'm at step k if I had an approximation at step k minus 1. I want to take my approximation that I had at step k minus 1, and I want to update it in some clever way to get a reasonable approximation when I'm at step k. That's what makes Quasi-Newton methods fast. So here are the two most basic ones. There's DFP and BFGS. These are just acronyms that stand for the names of the authors. So I never remember the names of the authors, but I always remember BFGS. David and Fletcher Powell came first, so the DFP method came first. This was, I think, probably the big breakthrough in Quasi-Newton methods. The idea is to take an approximation of the Hessian that's given by looking at where you were in the previous iteration, looking at your approximation of the Hessian in the previous iteration, and then performing a rank 2 update. So adding 2 rank 1 matrices to that previous H. And you can see that you can motivate it by a Taylor series expansion. So there's a bunch of work. There's books on these kind of methods. I would recommend that you read them if you're interested in the details. It's really a Taylor series approximation, and you use gradients, outer products of gradients, to approximate the Hessian. The cost is n squared for computing these updates, generically. So every time you apply one of these updates, instead of having to solve a linear system in the full Hessian, which is n cubed operations, you form an approximation of the Hessian and n squared operations, and it also costs n squared operations to solve. Are people familiar with the Sherman, Morrison, Woodbury update formula? Have you guys seen that in other classes? No? I thought maybe some of the statisticians would have seen it. So if you want to solve a linear system, suppose I have an invertible matrix A. I know A is inverse. And I want to solve a linear system that looks like this. And I know something like the inverse of A. Then there are very fast ways to compute a linear system in A plus a rank 1 matrix if I know the inverse of A. So we actually talked about that a bit when we talked about the QRT composition as well. You could form a QRT composition of A, and there's a fast way to update that if we add a rank 1 matrix. So all of these Quasi-Newton methods are very intimately tied to numerical linear algebra because they rely on tricks like this. BFGS came later, and I'd say it's much more widely adopted now. I don't think very many people use DFP anymore. The idea is the same. We're going to take an approximation of the Hessian that we had before. We'll take outer products of gradients in some sense to form a new approximation of the Hessian. Doing that's only n-squared computations. And we can also solve a system in the new Hessian, approximate Hessian, in n-squared computations. So it's much faster than a single Newton step. This one is quite popular because it's also a limited memory version. So there's something called LBFGS, which you might have seen. And in this version, you don't actually even store the full H that's been propagated over the entire history of iterates. You only store kind of a short-term memory version of H over the past, say, m iterations. So you would have seen this term thrown around a lot, LBFGS. For example, when people talk about quadratic programming, this was very, very popular at one point. I think it's still widely used, but maybe just not as actively researched. OK, so just maybe the main thing to remember is that there's an alternative to the Newton method called Quasi-Newton methods. Go look up BFGS if you're interested in learning more, implementing it yourself. They approximate the Hessian by H, where H is something that's cheap to store, and also it's cheap to solve linear systems in H. Questions about Quasi-Newton methods? Yeah?
Are there popular algorithms that optimize without an online fashion that only looks at a few examples of the data instead of computing the gradient and the tensor for the entire data set?
So you mean stochastic Quasi-Newton methods? Yeah, that kind of combination has been seen too. I'm not sure if I have a reference for it in the slides, but certainly that kind of thing has been looked at. Pretty much any combination of words from the stuff we've looked at exists in some form. So yeah, doing something like a stochastic Quasi-Newton method is also quite useful when the data is just enormous and can't be fit into memory. Good question. Other questions? Yeah?
So for Newton method, you provide function, the gradient, and the Hessian.
Right.
That's expected from the function. So what is expected of the Quasi-Newton method? Do you provide a rank 1 update?
It uses only gradients. So maybe I should have been more clear about that. All it uses is gradients of the function. So it uses gradients to approximate the Hessian. OK. So let's jump into the barrier method. So before we talk about the barrier method, I wanted to kind of give you this high-level overview, or this high-level preview, in a sense, of what we're about to talk about today. You can think of there's a hierarchy of second-order methods. And it looks like the following. Quadratic problems, excuse me, so let's just minimize a quadratic without constraints, are the easiest to solve. And in a sense, we have a second-order method for that. I'm calling it second order because it uses the Hessian. Right? What's the Hessian of a quadratic function? It's just whatever the quadratic form is. And so we can do that in closed form. If you ask me to minimize, say 1/2 x transpose qx plus b transpose x, then the solution is minus q inverse b. I can think of that as a second-order method. It's not really a second-order method, right? But I'm using the Hessian. That's why I'm calling it that, cubing the Hessian here. So that's very easy. It's the easiest problem to solve. We have a closed-form solution. Just came from taking the gradient, set it equal to 0. How about equality constrained quadratic problems? That's the next level up in the hierarchy. So they're still easy because we can use the KKT conditions to solve those in closed form. Remember we said that if we have an equality constraint, we can form the Lagrangian by adding a dual variable transpose, say ax minus b, if the equality constraint is ax equals b, and the KKT conditions provide us with a closed form solution of that. We just enlarge the quadratic form in a sense by, instead of solving a linear system in Q, remember we saw that we have to solve a linear system that looks like this. If our dual variable is being called, say, u or v, then we solve this linear system. If we had ax equals b, this is the negative gradient. And this would have been, right, so let's suppose that we were to minimize this problem, right, minimize 1/2 x transpose qx plus, say, c transpose x subject to ax equals b. We saw, or let's say, we saw that basically it comes down to solving a system like this from the KKT conditions. That's what we saw in previous lectures. Okay, so we can do quadratic problems. We can do equality constrained quadratic problems. Both of those are easy. What's the next level of the hierarchy? It's smooth problems. So if I have a function that's doubly smooth with equality constraints. And I can use Newton's method to solve that. So we learned last time. And why is that the next level in the hierarchy? It's because we basically turn those into a sequence of equality constrained quadratic problems. Right? At every step, I take a quadratic approximation of the Hessian. I solve an inner problem like this one. I can do it in closed form. And I solve a sequence of those to solve a problem that looks like this. Right? Minimize f of x subject to ax equals b. I turn those into a sequence of these problems with Newton's method. Okay, so that hopefully should be clear to you after the last lecture. The very next level in the hierarchy is generally constrained. So if I have inequality constraints, and my function is doubly smooth. This is the most general problem you like to solve with the second order method, right? The function being doubly smooth, that's, of course, an assumption that we're going to make when we talk about second order methods because they use the Hessian. And we use interior point methods to solve those problems. So that's the next level, right? Looks like minimize f of x subject to ax equals b. And maybe we have constraints that look like, so say hi of x is less than or equal to 0, I equals 1 to m. We solve this problem by turning it into a sequence of equality constrained smooth problems. So we're going to get rid of the inequality constraints by using what we call the barrier function, a log barrier function. Okay, so we're kind of building up on this hierarchy. These are the easiest problems to solve, quadratic problems. These are kind of the most difficult problems to solve, but they're all very related. It's what we're trying to understand based on this hierarchy. So what is the log barrier function? Let's just get specific. If we have a convex optimization problem like the following, it's the one I wrote down here as well, where our criterion function f is convex and twice differentiable, and so are all of our constraint functions. Hi of x is less than or equal to 0. And we have equality constraints as well. It looks like ax equals b. Then we define a function they call the log barrier function for this above problem. It maybe looks a little bit funny with two negatives, but I think it's really a very natural definition. We take each of the constraint functions, and we add a term that looks like log of minus hi of x. So let's look at this individual term. If hi of x always has to be less than or equal to 0. So this is always log of something that's non-negative, so it's well defined, right? And if hi of x gets close to 0, then what happens to this log function? It goes to minus infinity, right? So that's why we take a minus on the outside. We want the barrier function to be something that approaches infinity as one of these constraints approach violation. and otherwise is something that's well defined, and we're going to try to make it small as well. Okay, so this function phi of x is called the log barrier function. It's just given by taking minus the sum of all the logs of the negative constraints. The domain of this function phi, right, it's only defined on the set of points for which we have strict feasibility. Right, we have to have hi of x is strictly less than 0 for all I in order for this to be well defined. So where does it come from? It comes from essentially the idea of approximating indicator functions by these log barriers. That's really one way you can think of it. So let's ignore equality constraints. Everything's going to go through with equality constraints. In fact, we'll pretty much ignore them for the rest of the lecture because we know how to do Newton's method with equality constraints. So as long as we can get rid of inequality constraints, we're kind of in good territory. So the function f of x plus the sum of the indicators of these constraints being violated, right? The sum from I equals 1 to m of the indicator that hi of x is less than or equal to 0. That's another representation. Minimizing this function is another way of representing this minimization problem without the equality constraints. Right? We know that already. I can always just represent some constrained convex problem or just some constrained problem in general by turning the constraints into indicators. Each of these log barriers is actually trying to form a smooth approximation to this indicator function. So if you look, this is the indicator function, right, that say u is less than or equal to 0. It's equal to 0 when u is less than or equal to 0, and then it's going to jump up to infinity when u is positive. That's what this dotted line is showing. What I'm drawing here is actually the log barrier. So this, what I'm drawing is minus the log of minus u times 1 over t. I'm multiplying I'm multiplying these curves by 1 over t for different values of t to show you how it behaves. So let's draw the indicator function. It looks something like this, right? This is the indicator function that u is less than or equal to 0. Say here 0. This is the indicator function that u is less than or equal to 0. Let's draw one of these log barriers. Let's suppose we take t equals 1. Maybe it looks like this. Right? This maybe is what the log barrier looks like for t equals 1. As I take t bigger, what happens to this curve? So what happens if t is 100? Yeah, so we're going to get something that's actually quite squished. So first of all, it's not going to grow as quickly, and it's also going to go to infinity quicker. You can see that, for example, by taking derivatives. So as I make t larger and larger, this log barrier approximates the indicator function. Right? So you can think about, maybe we'll add something like 1 over t times the log barrier function to our criterion. We'll think of that as a smooth approximation to the indicator function, which in turn is equivalent to having the constraints. And we're going to think about trying to take t to be large, right? Because as we take t to be large, this gets more and more like the indicator function. An important property is that for any value of t, whether t is 1 or 0.1 or 10 or 100, the log barrier function always approaches infinity as one of the constraints approaches being violated, right? Or actually being tight. If one of the constraints approaches, if one of the hi's approach 0, then no matter what the value of t is, this is always going to approach infinity. Okay, that's a property just of this simple function that we call the log barrier function. Okay, so today we're going to talk about the following things. We're going to learn what's called the central path, which is given by varying t in the log barrier function. We're going to talk about some properties, interpretations of barrier functions in the central path. Then we're going to learn the barrier method. We're going to briefly talk about its convergence. And we'll talk about feasibility methods at the very end. Yeah, Sammy.
As t goes to 0, does that function approach the same function or the indicator function?
As t goes to infinity.
Does it approach the indicator function?
Yes, yeah. Okay, so by the way, you're going to learn a lot more about interior point methods in the next 2 lectures. This is the first. So there's a lot more to learn about interior point methods. We're going to learn something called the primal dual interior point method the week after spring break. The barrier method, I think, is simpler. And I like the barrier method, but I think some people who work with interior point methods, they think it's maybe not quite as efficient. So we're going to learn kind of the full spectrum. So this is going to be helpful for what comes later. Let's do some calculus of the log barrier functions. So we're going to try to compute its gradient and its Hessian as well. You can guess why. Why would we want these quantities? What do you think the strategy is going to be that we're going to use? We're going to put the log barrier into the criterion, remove the constraints, and then we're going to use Newton's method to solve that problem. And so we're going to want to know what its gradient and Hessian are, just for that reason. So this is the log barrier function, right? It's the minus sum of the logs of the negative constraints. And let's write down its gradient and its Hessian. This is just straight the chain rule. So if you're having trouble seeing why this is true, then make sure you look at Nicole's. She has some, refresher notes on calculus that she put on the class website. So the gradient of this function, right? Let's take the gradient and just think about each term, because the gradient's added. The derivatives are additive. I can always move it through the sum. All I look at is 1 over hi of x times the gradient of hi of x. And again, this is just like univariate calculus, right? So if this wasn't multi-input, if it wasn't going from r into r, then you just would put 1 over hi of x times hi prime of x, but this is just obviously the vector version of that. And the Hessian, again, just comes from the chain rule. We have to take, in a sense, derivatives with respect to this quantity now, and we get 2 terms from the product rule. The first term looks like 1 over hi squared times the outer product of the gradient with itself, gradient of hi times the gradient of hi transpose. And the second term looks like negative 1 over hi of x times the Hessian of hi of x. Okay, so those 2 quantities are going to come in handy when we do Newton's method with the log barrier function in the criterion. So let's talk about the central path. Central path is, I think it's a pretty interesting quantity. What we're going to do is we're going to add the log barrier function to the criterion times 1 over t, and we're going to get rid of the inequality constraints in our problem. An equivalent way of posing that is just to multiply the criterion by t and add the log barrier function to that, right? So if I multiply this by 1 over t or multiply this by t, it's the same thing. I'm minimizing the same problem. And the equality constraints are going to remain there. But like I said, if it makes it easier for you, you can actually forget about them for the whole lecture. They don't actually end up mattering. The central path we're going to define is the solution to this problem as t varies. So it's actually a solution path. We're going to write it as x star of t, as t varies from, say, positive, just bigger than 0, all the way up to infinity. Each point on the solution path, right, x star of t, is characterized by the KKT conditions. We can just take the KKT conditions for this problem. We can write down necessary and sufficient conditions, right, for x star t to be optimal. They are the following. This is just primal feasibility, right? Of course, it has to satisfy the equality constraint. We have to have that hi x star t is less than 0 for I equals 1 to m. And this comes from stationarity, right? Stationarity here is given by taking the gradient of this with respect to x and setting it equal to 0 after we add a Lagrange multiplier times the equality constraint. Remember, we're assuming that both f and phi are twice differentiable, so this would usually be a subgradient in the KKT conditions, but now we can just take gradients because they're convex and differentiable. So let's do that. I get t times the gradient of f at the solution. This should look like plus the gradient of phi at the solution. Remember, that was just this. So I'm just evaluating the gradient of phi at the solution. That's this part here. Plus, I had a term that looked like, right, w transpose ax minus b. When I added that to the criterion to form the Lagrangian. And so the gradient of that with respect to x is just A transpose W. So if this is true for some dual variable W, then that completely, if these three conditions are true, that characterizes the solution x star of t. And as t approaches infinity, our hope is that x star of t approaches x star, which is the solution to our original problem. All right, we don't actually have any proof of that yet. It's just kind of an intuitive hope. It seems like it should make sense. As t gets bigger, you can think about like having the 1 over t in front of the phi of t. That's approaching the indicator function, so the solution to this problem should approach the solution to the constrained problem. Right? If the world was just, that seems like it should definitely be true. So a very important example of the central path comes from linear programming. Like many things, linear programs were the first place in which the interior point methods were developed. So linear programming was kind of like the ground for development for a lot of methods. We also saw that duality came out of linear programs as well. Interior point methods came out of the linear program paradigm. That's where they first were seen. So let's suppose that our criterion function is just something linear, C transpose X. I'm not writing down any equality constraints here. Let's suppose that we had a linear constraint, some matrix D times X is less than or equal to some vector E. So suppose that these were our constraints. So minimizing C transpose X subject to this polyhedral constraint, our linear program. What does the barrier problem look like, the one we just wrote down? We add the log barrier function to the criterion, and we multiply the existing criterion by t. And so that's minus the sum of the logs of EI minus DI transpose X. Right? Because our constraints look like, say, DI transpose X is less than or equal to EI for all I. So in particular, let's look at the stationarity condition. Let's look at this one right here. We sometimes call that, by the way, the centrality condition. So these are just the KKT conditions. This is just the stationarity condition. But when we talk about the central path, we often refer to this as the centrality condition. And these solutions are often called central points. It's just no terminology. So that looks like t times the gradient of the loss, right? Which was, now it's just c, plus the gradient of the barrier function. What is that? It's minus the sum over all I of 1 over this quantity, 1 over EI minus DI transpose X, times the gradient of this quantity, which is just, actually it's the gradient of the negative of this quantity, right? Because this is minus HI, and so that's just DI. So if this is true, right, for some vector x at a value t, then that characterizes the solution, x star of t. And I think it's actually quite nice to interpret this if we think about what this means geometrically. This means that the gradient, right, this is the gradient of the barrier function, this guy right here. This has to be parallel to minus c. That's what this condition is saying, right? I write this as, say, minus t times c is equal to the gradient of phi. So we're saying that the gradient of the barrier term has to be parallel to minus c. And let's take a look at this picture, see if I can reproduce it. So let's suppose this is the constraint dx is less than or equal to e. That's my polyhedral constraint. What is being drawn in the dotted lines are actually the contours of the log barrier function, say the 90th contour or something, as 90th percentile, as t increases. So this might be the contour when t is 10. The central path, it's going to look like the following, this example. Say this is computed numerically. So we start off, say, at x star of something very small, like 0.001. We get to maybe this point, which is x star of, say, 10. And in the limit, as t gets bigger and bigger, this should be x star, which is the solution to our original linear program. This condition, right, stationarity condition, is saying that if I look at the gradient of the barrier function at the solution, so say I have t equals 10, the gradient we know, remember, points orthogonally to the direction of the contour, to the shape of the contours, that has to be parallel to minus c. So if I'm looking at c, c should be pointing in this direction, right? This would be determining the criterion. C transpose x in my linear program. So I'm saying that the gradient has to, at any point on the central path, has to be parallel to the gradient, the negative gradient of the criterion. It's actually maybe easier to interpret that in the kind of orthocomplement space. That means that the hyperplane that passes through the solution and that's tangent to the contour, so this guy right here, has to itself be parallel to the hyperplane that looks like C transpose x equals, say, C transpose x star. So this guy here is that hyperplane. So the gradients being parallel is nothing more than these two hyperplanes being parallel. So as we move along the central path, we're going to be, these contours are going to be getting closer and closer to the full polyhedron. And the solution at any point is characterized by this geometric condition, right? Wherever we are next, it has to be a spot on the contour where, if I look at the tangent plane to that, it's parallel to the hyperplane essentially determining the solution. C transpose x equals C transpose x star. So now you can see why the barrier method is called an interior point method. It's because we're starting with an interior point, and we're following the central path until we get to the solution, say, of our linear program, which lies on the boundary of the constraint set. And when interior point methods were first developed, it was this kind of geometry that played a big role. It's how people thought about creating interior point methods in the first place. Okay. Any questions about the central path before we move on? No. Yeah, so you mean, is it a linear, piecewise linear or something, or is this?
No, just linear. Has t big.
Well, you can kind of see from my picture, which is not an actual solution path, that it's not. But this picture is an actual solution path. So this is an actual central path. So they're not linear. They're smooth as a function of t. But you can kind of see that the role of t, right, it's a nonlinear relationship that's being determined here, right? If we look at x star as a function of t, it's not going to be really determined linearly in terms of t. So the solution to this equation for each t determines the central points. Yeah?
Why do we care about the solution path? Why don't we just care about the value, the solution where t is very large?
Yeah, that's a good, I mean, it's a good question. In a sense, from a pure optimization perspective, we don't. We just care about the solution when t is very large. But we're going to see that we can't actually really disentangle the two. So the central path is important because it gives us, because its limit is the solution. Okay, the following is a very useful fact to realize, and now we're going to bring back in duality. It turns out that we can always derive feasible dual points from the central path. These are dual points for the original problem, not for the central path problem, not for the barrier problem, for the original constraint problem. We can always, from a solution of the central path problem, we can derive a feasible dual point. What is that going to enable us to do for the original problem? We have a primal feasible point and a dual feasible point that we get right from the central path. What can we do from that? So what was one of the uses of duality we had? What happens if we evaluate their criterions? Right, the duality gap. So if we use that pair to take a duality gap measurement, then we know that actually bounds how far we are from optimal with respect to the original problem. It's a very, very useful characterization that we get from the central path. So it's actually not very hard to define them. So remember, we had these KKT conditions here. I'll just write them out again, because we'll do a little bit of work on the paper. right, ax star at t equals b, and hi of x star t is less than 0, I equals 1 to m. And we had the stationarity or centrality condition, which is t times the gradient of our original criterion plus the gradient of the log barrier function, but that looks like the following. Right, 1 over hi x star t times the gradient of that constraint function plus a transpose w equals 0. Okay? And this has to be true for some w. If A is an m by n matrix. Yeah. I guess I'm not going to use m because I already used m for the constraint set. So let's say A is an R by n matrix. OK, so we know that basically at any point in the central path, this is true about the central point from the KKT conditions. Now we're going to define a dual pair. We're going to call that u star of t and v star of t. So we're going to define these according to the following. The components of u are going to be defined just by taking essentially what we see in front of this gradient term here, minus 1 over hi of x star of t. And the components of v are just going to be defined by rescaling whatever this vector w that made this true in the first place for the central path. So now the claim is that actually u star and v star are feasible for the original problem. Right, that was this one, minimize over all x f of x subject to these inequality constraints and equality constraints. Okay, so how do we do that? Well, we have to check, first of all, that these are dual, we have to check that, first of all, these lie in the domain of the Lagrange dual function. And second of all, that we actually have the right sign for the components of v. So let's do that. The first one, I'm sorry, for the components of u. Right? So we're going to, basically, you can see v is going to serve as our Lagrange multiplier for the equality constraint. U is going to serve as the Lagrange multiplier for inequality constraints. So we have to check that the signs of u are correct. So we'll call this one the sign check. We have ui star at t, which is equal to minus 1 over hi of x. That's going to be actually strictly larger than 0, right, for all I, because of the fact that x star of t was strictly feasible. So the sign check is done. The second thing we have to check is that they lie in the domain of the Lagrange dual function. So this one's a little more subtle. This one is immediate, right? This one is a little bit more subtle. So remember, when we're minimizing the Lagrangian, we get the Lagrange dual function. The domain of the Lagrange dual function, right? So g of uv is defined as the minimum over all x of the Lagrangian, L x uv. The domain of g is all points uv with u bigger than or equal to 0, such that this minimum is bigger than minus infinity. So this is something we've been doing all along. We haven't maybe made it explicit. Actually, I think I did say this explicitly in the duality lecture. But remember, when we minimize the Lagrangian, sometimes we get something that goes all the way down to minus infinity. We add a constraint then to the dual problem. That's how we added constraints. Right? If there's like a linear term transpose one of the dual variables, linear and x, then we added some constraint that looked like a linear constraint on that dual variable. Another way of looking at that constraint is that actually that's determining its domain, the domain of the Lagrange dual function. So we have to check that this u and v are in the domain of the dual function, which means that it's, when we minimize Lagrangian, it's bigger than minus infinity. We don't have this trivial case. And we can do that because we can actually check that if we plug in u star of t and v star of t, then this is minimized, I claim, at x equals x star of t. And so if it's minimized at a particular point, that means that implies that we're not achieving a minimum of minus infinity, right? Because we're not sending off x in some direction to achieve a minimum of minus infinity. So that would check that this, if we check this was true, that would ensure that u and v are in the domain of the Lagrange dual function. And this also comes directly out of the way we've defined them. So there's not really anything to check here either. Let's just go back up to the centrality condition, the top. So the centrality condition said that t times the gradient of f plus the gradient of phi plus a transpose w is 0. Let's just divide everything by t here. Okay? So we're going to divide w by t, and we're going to divide this part by t as well. And the definition of u, it looks like I missed out a t. So you'll see why we need it. Now, look, this is just simply ui. I'm going to do a plus and a minus there. This is just simply ui of t, and this is just simply v of t. And so by construction, we know that they minimize, that if I plug in, ui star here and v star here, that x minimizes x star of t minimizes the Lagrangian over all x because of this condition. All this is saying is that the gradient of the Lagrangian with respect to x is 0. So this is another way to motivate their definition. Right? I'm trying to form these dual variables so that x star of t minimizes the Lagrangian. So that just comes from the centrality condition. Any questions about that construction? Okay. So this is going to allow us to do what we described before, which is compute a duality gap between the primal criterion at x star of t and the dual criterion at the pair u star v star of t. And we're going to use that to tell us how far we are from optimality in the original problem. Because remember, we're talking about the original problem now. So u star and v star are feasible, dual feasible points for the original problem. And of course, x star is feasible for the original problem as well. That's, we construct all the points along the central path so they are always primal feasible. So let's just look at what the dual function at u star and v star looks like. We said that, well, x star of t minimizes the Lagrangian when the dual variables are u star and v star of t. So we can just evaluate the Lagrangian at x star to get the dual function. Right? This is the minimum of the Lagrangian when I plug in x star of t. And so now we see, right, let's just f of x star of t plus the sum of ui star of t times hi of x star of t. This is defined to be minus 1 over t times this quantity. So this quantity is just summed up, it's just minus m over t. This quantity is 0, right, because we're, of course, primal feasible, so this difference is 0. that means that the Lagrange dual function, by the way we've constructed it, evaluated the dual feasible pair, is always the primal criterion at x star of t minus m over t. It's a very clean construction. It tells us that when we take the difference between f of x star of t and this, that should give us an upper bound on how far we are from being suboptimal. So the duality gap is just m over t, and that means that at any point in the central path, the primal criterion for the original problem at x star of t minus the optimal primal criterion value is less than or equal to m over t. So this is like about the nicest form of duality gap we can have, because usually the duality gap actually requires some kind of computation. We actually have to maybe produce a feasible dual point or something. This is an example where there's no computation needed. If you're on the central path, you have m constraints, and you're looking at the barrier parameter t, your duality gap is m over t. So you're m over t away from optimality. It's a very clean construction in a special case that we got by defining these dual feasible points very cleverly. So we can use this as a stopping criterion, right? If we're along the central path and this is less than epsilon, then we know we're less than epsilon from the solution we actually want. It also confirms this intuitive fact that I claimed was true, which is that if t goes to infinity, then x star of t should approach a solution. Right? We can see that right from this duality gap right here. As t goes to infinity, the duality gap goes to 0. So x star of t should approach a solution x star. Okay, so I think duality, once again, gives us something very powerful. The arguments here are super simple. I mean, we're just defining dual variables in a very simple way. There's nothing kind of complicated about their construction. Another way in which kind of duality gives us something very powerful. So there's another way to interpret the central path, and that has to do with an interpretation via what we call a perturbed set of KKT conditions. This kind of interpretation is interesting. It also leads to the primal dual interior point method. So this is one of the motivations for doing an interior point method differently, which is what you'll learn the week after spring break. So the central path solution x star of t, right, and the corresponding dual point u star v star of t, they solve the following set of conditions, which we'll write down. They solve the stationarity condition. We checked that directly. That's actually by definition of the dual feasible points. This is true. You can think of, we defined them according to the goal that this should be true. They satisfy, by construction, each ui times hi of x is equal to minus 1 over t, right? Because this was defined as minus 1 over hi times t. The primal point is primal feasible, right? All the constraints are less than or equal to 0, and the equality constraints are met as well, ax equals b. And lastly, the dual points have the right sign. So what is this set of conditions, if we think about it? This is very close to the KKT conditions for the original problem. We've almost constructed a primal and dual pair that satisfy the KKT conditions. What's the only difference? Right? This is stationarity, the first one. These are primal feasibility. This is dual feasibility. The only difference is that this second condition here is not quite the complementary slackness condition. We should have ui times hi of x is equal to 0. We have it being equal to minus 1 over t. Well, the sign is correct here because ui is always positive and hi of x is always negative, so it should be negative. It should be less than or equal to 0 always. Complementary slackness tells it has to be equal to 0 at the solution. We've produced a point on the central path that satisfies this equal to minus 1 over t, not equal to 0. So it's like we've taken the KKT conditions, and instead of actually solving them, we've just moved the complementary slackness condition a bit. We've perturbed it slightly. And if t is large enough, then this perturbation is pretty small. So it's another way of convincing yourself that we've solved something very close to the KKT conditions, so we should get something very close to the solution. And that analysis shows us that as t goes to infinity, this complementary slackness condition approaches 0. So we're really solving the limit, the KKT conditions. Another way of maybe convincing yourself we should be getting the solution to the limit as well. This kind of argument, this kind of perturbation, the KKT conditions argument, like I said, it leads to other ideas for interior point methods. I think it's quite popular in that regard too. Do you guys have questions? This is it's been quiet, but it's difficult material, so make sure you pipe in if you have questions. Yeah, Justin.
Clarify what you meant by the duality gap with the M over T as a stopping criterion?
Sure. So we'll see that when we talk about the actual Berry method. But we might do something like I haven't motivated this yet, but we might do something like solve the barrier problem for a really small value of t by using Newton's method. So minimize this using Newton's method for a small value of t, make t bigger, solve it again, make t bigger, solve it again, make t bigger, solve it again. And we might stop that process when m over t is less than epsilon, because we know that wherever we stop it, the duality gap is less than epsilon, which tells us that the distance we are from optimality is less than epsilon 2. So in that sense, it can be used as a stopping criterion. But we'll see the Berry method in a few slides. So let's get to an algorithm now. Let's actually get a first attempt at an algorithm. So this goes to the question that was just asked. We've seen the solution of this problem, the Berry problem, is no more than m over t suboptimal. So why don't we just pick some epsilon? Right? Suppose I want to get a solution to within 10 to the minus 5 accuracy. So epsilon is 10 to the minus 5. I have a bunch of constraints, m of them. So I'll just set the barrier parameter to be whatever I need to, so that m over t is less than or equal to epsilon. In other words, I'll take t equals m over epsilon. And I'll just solve that problem with Newton's method. Just go and solve this problem with Newton's method, and I'll declare victory because whatever I get is going to be within epsilon of the solution by all of our constructions so far. In terms of the criterion value, right? F of x star of t minus f of x star is going to be less than or equal to epsilon. So that's not a bad idea. In fact, that's what people tried maybe as a first attempt before interior point methods. But the problem is that the required t you need is often huge, and that causes serious problems with this approach. Right, so if I have, say 1,000 constraints and I want 10 to the minus 6 accuracy, then I need t to be 10 to the 9 in order to make that work. That's just not a very good scaling. It's numerically unstable when you do that in practice. I have to take stuff like, when we do Newton's method, we're going to be taking gradients and Hessians of this thing, and we're going to be trying to solve linear systems in that. If one of the terms is multiplied by 10 to the 9, it's going to be very numerically unstable. If we just start off kind of from an arbitrary starting point, that tends not to work well at all. And I say this method is almost never used. A better approach is to traverse the entire central path in order to reach the end. So the central path is really just an object that we study because we care about its endpoint. And it has kind of a better stability property than what we get if we just chose t to be big. We just had some initial guess at the solution x naught and performed Newton's method straight out with that large value of t. So we're going to try to solve this problem, say for a small value of t, make it until we converge. Then we're going to solve the problem for a little bit larger value of t. And to start off that next run of the algorithm, we're going to take our solution when t was small and start it there. And then we're going to make t larger, and we're going to take our previous solution, start a new algorithm at that large value of t, etc. And we're going to repeat that. And if we increase t in a certain way, then hopefully the solutions, each time we run Newton's method to say compute solutions at bigger and bigger values of t, it doesn't take too long because we're starting in a spot that's kind of close to the solution already. And we know that if we do this and we get to a large enough value of t such that m over t is less than or equal to epsilon, we can stop. So that's the in-words version of the Berry method. Traverse the central path at a bunch of t's using Newton's method each time. What does that remind you of? This kind of idea, solving the problem for a bunch of different values of this parameter t. With what are we doing? We're kind of using warm starts, right? It's not really this exact same thing because we don't actually care about these solutions for all the values of t. We only care about the end. But we are kind of using a warm start strategy. We're solving it. We're using that to initialize the algorithm at the next value of t. that reminds you probably of the solution path to one of these statistical optimization problems where t is not something that we defined from the optimization perspective, but t had a statistical meaning, right? So if we're minimizing a generic loss plus regularizer type statistical problem, right? I'll use beta to think of us being in the statistical or machine learning world, right? We might be solving this type of problem, solve this over lambda. In fact, the central path is very closely connected with this idea. And the central path is a lot older idea than solution path algorithms and statistics. What I did here was I just drew the linear programming central path as t goes from really small to really large. And I also drew the ridge regression solution path. So here I'm doing ridge regression, so that means that the loss is, say, y minus x beta squared. And the regularizer is, say, the L2 norm of beta squared. And I'm drawing for you the ridge regression solution path as I vary this parameter lambda. So if lambda is, say, what I'm actually drawing is the solution of the constrained version of this problem, but we know that they're equivalent, right? So if I take beta squared is less than or equal to t, then I was solving the constrained version of ridge regression because I wanted to draw for you the contours. So if t is very large, then we're just solving unconstrained least squares. As t gets made smaller and smaller, for example, we're getting more and more shrunken solutions. Here I'm drawing the contours of this L2 ball in 2 dimensions. So it's the 2-dimensional example, beta 1 and beta 2. Right, this is the set of all points for which the 2 norm of these two is 1.22. I'm just showing you that is a solution path very much like the central path. And we actually approach these problems very similarly algorithmically as well. Right? With this statistical solution path, we solve a problem kind of in the easy regime, and then we use that to warm start the solution when we change the statistical tuning parameter, etc. I don't think this connection is developed as it could be. I think that most statisticians for a long time were not aware of the central path construction. But I think there is a lot that can be said connecting the two. And I think it's a very interesting topic I just wanted to point out to you. It's very underdeveloped. So after that caveat, let's get to the actual barrier method. So the barrier method, we're going to solve a sequence of barrier problems, these type problems, as t increases until we get t over m less than or equal to epsilon, because that's our duality gap stopping criterion. We start at some value of t, might call it t naught. We're going to solve this problem using Newton's method, and we're going to get something from that, which we're going to call x naught, which is just the solution to this problem when t was t naught. Then we're going to use a scheme for increasing the barrier parameter. This barrier parameter is t. I probably shouldn't have called this the barrier parameter as well. We're going to use some scheme for increasing t. The scheme we're going to use is we're going to choose some constant, mu. Let's say mu is 2. And we're going to multiply the value of t we're looking at by 2 each time. So we're going to now solve the problem at 2 times t naught using Newton's method to produce a solution, right, at that value of t. And we're going to initialize Newton's method at the previous point that we visited along the central path. So according to the picture, wherever the picture is I drew, we might have, as we increase the barrier parameter, you can think of this pushing us farther and farther out along these contours. Each time we solve one problem, like say this problem when t is 10, we initialize that at the solution that we saw at the previous value of t. And t is being multiplied by mu each time along the central path. So that's the algorithm. We stop when t over m is less than or equal to epsilon, and if not, then we're going to update t by multiplying it by mu. The first step we call the centering step. because it brings this iterate on the central path. Again, it's just terminology. I might also sometimes call this the inner loop, right? This is like inner iterations are iterations of Newton's method. Outer iterations are iterations of this algorithm, just to be clear. So what are some considerations that we might have in mind? There's two you can think of: choice of mu and choice of the initial parameter t naught. So let's think about choice of mu first. If mu is too small, then there's many outer iterations that might be needed. Right? If I only increase the barrier parameter by something like 1.1 each time, then I have to do that many times to get it to be large eventually, and so I might take too many iterations. If mu is too big, then Newton's method might take many iterations to converge compared to if it was small, because each time the initial starting point is very far from where the solution is going to be at the next step. Right? In this picture, if I went from here to this contour, there's a big difference between where I'm starting and where the solution ends up. So there's a trade-off with mu. Same thing with t naught. It's really the same story. If you started off too small, then there's many iterations needed in order for it to get large eventually. If you started off too big, then the very first Newton's method solved, the very first centering step, may take a long time. So fortunately, practical implementations of the Berry method are often pretty robust to the choices of mu and t naught, and there are kind of somewhat standard recommendations that people have for these parameters. It is like backtracking, though, in that these are things you're going to have to choose when you implement the method yourself, and they can affect performance. It's just that the difference between mu equals 10 and mu equals 20 is usually not like an algorithm that's terrible or it's an algorithm that's great. So this was an example I took from the Boyd and Vandenberg book. They were solving a linear program in 50 dimensions with 100 inequality constraints. These are the number of Newton iterations required in total across the whole life of the barrier method in order to get the duality gap down to, say, 10 to the minus 6. And you can see that here's the value of mu they tried. Mu equals 2, mu equals 50, mu equals 150. So the difference between taking mu equals 2 and mu equals 50 is like maybe 60 iterations, which, it's significant, but it doesn't mean that this one's impossible and this one is easy to do. There's not a huge difference in the grand scheme of things. And the difference between mu equals 150 and 50 is not very big. So the standard recommendation is to take mu between 10 and 50. That's what Boyd and Vandenberg say. Again, I think these are things you'd have to try in your problem to make sure that they're on the right scale. Yeah?
So this form of updating study equals mu the array study. My question is why not something more conservative that increases quadratically or something?
It's a good question. It has been studied, and in fact, the convergence rates that we're not going to prove but we state, they depend on that form of update.
Does it also depend on mu?
Yeah, they depend on mu as well. Jersey. Yeah, I think it's a good question. So why Newton's method? Why not something else? I think historically, there's a couple answers. Historically, interior point methods were built on top of second order methods, so that's why people use Newton's method with them. But a better reason is that practically speaking, if the centering steps are not performed to high accuracy, then you can kind of diverge from the central path. You can fall off the central path. So you want to use a method for the centering steps that can give you high accuracy solutions. And so that's why people use Newton's method. If you use something like gradient descent, then there's not really that guarantee. OK, good questions. Let's talk about the convergence analysis and what you get out of it. So we're going to assume we can solve the centering steps exactly without any error. Now, like I just mentioned in Jersey's question, there are other results that say that if the centering steps are performed to high accuracy, you still get this rate. But those are just a little more sophisticated. We're not going to state them. But the following result is immediate if we can solve the centering steps exactly. Right? After k centering steps, the Berry method is going to satisfy the following bound. F of xk minus f star is equal to m over the value of t that you're at after k centering steps. Right? That's just the duality gap bound. This should be m over tk. What is tk? It's just mu to the k times t0 from our updating scheme. If we flip this around and we ask what value of how many iterations do we need to get to a certain level epsilon of accuracy, you can see that we require log of m. It's essentially log of 1 over epsilon iterations, right? The constant, the barrier constant that we use to update mu appears here. The number of constraints appears here too, but the scaling with epsilon is log of 1 over epsilon. So it gives us a linear convergence rate in terms of the number of outer iterations that are required for the barrier method. Okay, so you shouldn't expect to have to do very many outer iterations. There's a lot more kind of fine-grained results than this. This is the most basic one. Like, you might ask how many Newton iterations in total are required, right? Not just how many outer steps are required, but how many Newton steps in total are required. The answer under kind of sufficiently general conditions is still log of 1 over epsilon. So you still only need log of 1 over epsilon iterations to get an epsilon accurate solution if you're talking about inner iterations, Newton iterations. There's also much more kind of tight bounds that can be made under self-concordance. And I think Javier will talk about that a bit when he talks about the primal dual interior point method. You can get rid of the dependence on some of these parameters if you think about self-concordance. Actually, I think it's not quite in this formulation, but if we talk about the number of Newton steps required, that gives you a much more precise answer. So if you're interested in that, you can take a look at the references I put at the end. You can also look forward to some of the stuff that Javier is going to cover in the primal dual interior point method. So here's an example of the progress for the barrier method for linear programming with the same number of constraints, with a growing number of constraints. We're trying to see how does the convergence of the barrier method depend on the number of constraints. From this bound, we see it should depend logarithmically on m, but this wasn't in the number of Newton iterations. This was the number of outer iterations. So you might ask, like we said earlier, how does the number of Newton iterations scale with the number of constraints? You can see it's still very slow. And the answer is still essentially log of m over epsilon under pretty general conditions. So if we solve a problem with 50 constraints versus 500 constraints versus 1,000 constraints, we only need something like 10 more Newton iterations or 15 more Newton iterations with the barrier method. So it scales well in that sense. Said differently, if you look at the number of Newton steps needed to get the duality gap down by a certain factor, it grows very slowly with m as well. So just another way of looking at it. That's it. Okay. The only thing we haven't really covered so far is that initial centering step. So there was actually something that was a bit subtle about the initial centering step, which is that in order to get that to work, we had to run Newton's method, right, at the value t0, starting at some point x0. That point x0 had to be strictly feasible, because we're going to add minus log of minus hi of x to the criterion. If it wasn't strictly feasible, if hi of our initial starting point was 0 or bigger than 0, then the criterion value is infinite to begin with. So it's not even a problem that we can approach. So for that very first centering step, we're going to need a strictly feasible point. You can see that after that, actually, by using warm starts, we are always strictly feasible. So we never have to worry about this problem except for at the start. So before you run an interior point method, you do something that's usually called a feasibility method. These are also called phase 1 methods, and the interior point method is usually called the phase 2 methods. So phase 1 is just find myself a feasible point. How do we do that? Well, we can actually use an interior point method to solve another problem. So it's really not much different than what we've been talking about already. We're going to solve the following problem. We want to find a point x for which these constraints are met strictly and the equality constraint is met. We're going to minimize over all points x and s the value of s subject to h of I is of x less than or equal to s and ax is equal to b. You can think about s as the maximum violation of feasibility, right? If we can solve this problem and at the solution s is negative, we've done great because everything is strictly feasible. If s is positive at the solution, then that's not good. So what we do before we run interior point methods is that we actually solve a problem like this. We can solve this problem with an interior point method. So we actually kind of run 2 interior point methods. Why is this one so much easier to solve than the first one? It's because a strictly feasible point is very easy to find here. You don't have to do a feasibility method for the feasibility method, because a strictly feasible point is very easy to find here. We can just take s to be very, very large, for example, right? And then we'll be OK. You can just start at any x naught and take s to be the maximum of all the hi's of x naught. So that is the complete picture for the Berry method. Solve the feasibility problem strictly to get the initial point and then run the Berry method as you saw it. On your homework, this homework you're turning in tomorrow, we gave you the feasible point. In a sense, you were kind of doing a bit of a Berry method in the last question, whether you realized it or not. The question on image denoising, it maybe looked more like a hack at this point because you hadn't seen the Berry method, but you kind of added something to the criterion. You didn't change the value of t. We gave you the feasible point, so we actually solved the feasibility problem initially ourselves. This next homework comes out on Thursday. You'll have to do them both together. OK, that's it. Make sure to turn your homework. Have a good spring break. And when you get back, Javier is going to do the next week of lectures. So you'll get to hear about primal dual interior point method.